Next, talk of another concept, the concept of stream function. A very important concept, a very useful concept. Let us study stream functions for only two-dimensional steady and incompressible flows, so that the equation of continuity del Vx by del x plus del Vy by del y is equal to 0 applies. Let S1, S2 and S3 be three streamlines. Streamlines do not intersect. Let us consider a small control volume within two streamlines S1 and X2. This surface coincides with the streamline S1, this surface coincides with the streamline S2. Surface 1 is normal to the velocity, and so is surface 2. As you know, a streamline is a line which is tangential to the velocity. So there is no component of velocity across these two surfaces. If the flow is steady and incompressible, there is no accumulation of mass within the control volume, and so the mass entering at 1 should be equal to the mass leaving at 2. Since the location of surface 1 and 2 are arbitrary, I could take the control volume anywhere between the two control volume. What conclusion can we draw? That the mass flowing within two streamlines is constant at all locations. So the mass flow rate here is the same as mass flow rate here, is the same as mass flow rate here. Everywhere we have the same mass flow rate. VA1 is equal to VA2, the density being constant. So the spacing between the streamline increases where the flow slows down and decreases where the flow speeds up. If area A1 is more than area A2, then V1 should be less than V2. This is illustrated very nicely by this example. Consider the creeping flow about a cylinder. A flow at very low velocities such that Reynolds number is much less than 1. This is a picture that we showed you earlier. The flow looks quite symmetric. There is no separation. If we mark a few streamlines, we see a central streamline going like this and another streamline go like this. The spacing between two streamlines here is less than the spacing there. So what does that mean? The velocity on the shoulder of the cylinder is less than the velocity upstream. The spacing here is the largest. So velocity here should be smallest. In fact, this point is the stagnation point where there is no velocity. If we draw the velocity profile at the shoulder, this is the velocity profile. Notice that even at substantial distance away from the surface, the velocity of flow is still less than the undisturbed velocity out here. We will talk about this later. On the other hand, consider the flow of the fluid which is non-viscous. There is no fluid which is completely non-viscous, but it is possible to simulate this flow in an apparatus called the Haley-Shaw apparatus, where the fluid behaves as if the Reynolds number is infinite. There is no boundary layer, there is no separation in this flow. Notice that in this case, the distance between two streamlines is much larger upstream than on the shoulder. What does this mean? This means the velocity on the shoulder is much larger than the velocity upstream. The velocity profile is like this. This is very close to the undisturbed velocity. So velocity at shoulder is much larger than the undisturbed velocity. Of course, in an actual flow, the velocity at the surface must be zero. So this velocity must have a very sharp reduction to zero velocity. This is what the boundary layer that we discussed earlier and which we will discuss later on in the course. Let's again consider the same picture. Three streamlines S1, S2, S3. The flow between S1 and S2 is moving towards the right as shown. Consider point A on S1 and points B and C on S2. Clearly the flow across AB must be same as flow across AC. So as before, the flow between two streamlines is constant. The two streamlines actually act like a conduit for flow. No flow crossing the streamlines. Now we can associate a function psi with streamlines such that d psi is psi S2 minus psi S1. Since if we associate a function psi with S1, then the value of psi with S2 would be d psi greater. Stream function psi is a function which takes constant value for a given streamline such that the difference of values of this function for two streamlines gives the flow rate per unit depth between them in two-dimensional flows. Let's look at this in further details. Consider a point P at location xy on streamline S1. The value is psi. Let's draw a vertical and horizontal line from point P to the next streamline S2. The volume flow rate across this must be same as volume flow rate across this. And this volume flow rate must be d psi because the value of the stream function associated with S2 is psi plus d psi. So d psi is the volume that flows between the two. Clearly d psi is Vy into minus dx, and which is also equal to Vx into dy, because it's only Vy velocity component which will create a flow across the horizontal line segment, Vx being along the line segment itself, and Vx would be the only component that will create a flow across the vertical line segment. This can be manipulated to give del psi by del y is equal to Vx and del psi by del x is equal to minus Vy. We can obtain these equations by formal mathematics also. Differentiating psi into constant gives you del psi is equal to del psi by del x dx plus del psi by del y dy is equal to 0, or del y by del x is equal to del psi by del x divided by del psi by del y from this equation along a streamline, because psi is constant. Now, but dy by dx along a streamline is nothing but vy by vx. So, minus del psi by del x can be treated as vy, and del psi by del y can be treated as vx. Same as before. Notice an important use of stream function. We can replace the two variables Vx and Vy by a single variable psi for incompressible steady flows in two dimensions. That reduces the number of unknown variables by one. Two variables Vx and Vy can be replaced by psi. This gives an important advantage in calculating complex flows. In case of two-dimensional cylindrical polar coordinates, the velocity components in the r and theta directions are given by Vr is equal to del psi by r del theta, and V theta is equal to minus del psi by del r. Psi is the stream function. Let's do an example. A stream function is given as psi is equal to 3x squared minus y cube. Is the flow incompressible? How can you find out the flow is incompressible or not from a stream function? Yes, we can find out the velocity component from the stream function Vx and Vy. Once we know the velocity component Vx and Vy, we can test with the continuity equation whether they satisfy the continuity equation or not. Vx is equal to del psi by del y, and here it would be minus 3y square, and Vy is equal to minus del psi by del x, and this would be 6x. Incompressibility requires delta Vx by delta x plus delta Vy by delta y is equal to 0, and this is satisfied, and so the flow is incompressible. Delta Vx by delta x is 0, delta Vy by delta y is 0, so that the continuity equation is satisfied and the flow is incompressible. There is a very interesting property of streamlines and stream function. Let us consider the function psi is equal to xy. Psi is equal to constant, that is xy is equal to constant lines are plotted in this xy plane, and they are rectangular hyperbolas of this shape. Vx is del psi by del y, which is x, and Vy is minus del psi by del x, which is minus phi. Now, we have stated that no flow crosses a streamline. So, if we replace the x-axis by a wall, then psi is equal to xy represents the flow in a half plane above the wall, assuming the viscosity is not there, assuming that the no slip condition does not apply. This is a particular kind of flow which will be considered later, called the irrotational or the potential flows. So psi is equal to xy can be used to represent the flow towards a wall. The flow coming vertically downwards towards a wall. And then the flow would split into two portions. This would be a stagnation point. The velocity would decrease as we go down and would increase as we go away from the origin in the two directions. Not only this, we may replace the y axis also by a wall, so that this first quadrant is the only region where the flow takes place. Psi is equal to xy, the stream function, also represents flow in a corner. This is a flow that comes here and goes towards this in one corner, with these replaced by solid walls. So what is the stream function of this corner flow? Psi is equal to xy. Simple. And the velocities can be obtained at any x and y by these formulae. Not just this, there is one more possibility. That we replace this streamline by a wall and replace this streamline, another streamline, by a wall. Then psi xy represents flow through this channel as well. And the velocities at any point x and y within this channel of this specific shape would also be obtained by differentiating the stream function xy. Thank you very much.